All right, this will be running a hypothesis test for paired data. It's page 137 of the note spirals. So we have the scenario. One indicator of physical fitness is resting pulse rate. 14 men volunteered to test an exercise device advertised on TV by using it 3 times a week for 20 minutes. Please note, it says volunteered. We're going to need to address that in our conditions. The resting pulse rates per minute were measured before the test and then again after 6 weeks. So we have a before, we have an after. That's indicating to me that we're probably working with paired data because we have a before and an after. And we have the results shown in the table below. And sure enough, I have each individual. And because I have each individual and I have their individual before and after, going, this is definitely a paired data situation. I have the information for each individual. And it's really important that I have the information for each individual. So take a moment and we need to go to stat edit. So stat edit. And in L1, I entered the before. So I entered the before data. And in L2, I entered the after data. So I have 2 lists of data. Like I said, I entered the before into L1 and the after into L2. So their question to us is there evidence that this kind of exercise can reduce resting pulse rates? So we're looking for reduce, all right? So the null hypothesis is always going to be mean difference equals to 0. Now the alternative, you need to take a moment, and this gets students sometimes. So we are going to go before minus after. And I could have chosen after minus before, but I'm going to do before minus after. Now, if I had a resting pulse rate of 72 before, they're wanting it to reduce, so I need a smaller number, which would be after. So let's just say this is what they're wanting to happen. It may not have happened, but this is what they're wanting to happen. They want this to go down. So this means this would be a greater than symbol. So my mean difference is greater than 0. Now I need to make sure that when I make my definition, I define before minus after. I have to say what order I'm doing. So let mu d equal the true population mean difference in resting heart rate before minus after. Now, if I said resting pulse rate, that's fine. And if I left off the 6-week exercise program, that's fine. But let mu d equal the true population mean difference in resting heart rate before minus after. That's what we're looking for, something along those lines. All right, our first condition, according to the recipe says it needs to be a random sample. Unfortunately, what I read is I had 14 volunteers. So I need to address that, and I'm going to random sample. Not a random sample, but we're going to assume that the men are representative of the population. Don't know that that's really true in this case because there are my students, but nonetheless, we have to make the assumption that they're representative of the population, or we really can't proceed. This is very rare that you'll ever have to make a comment like this. It's almost always going to be a given, but this one was not. This was not a given. We couldn't just say given because they're volunteers. We have to say that they're representative of the population. Then we need to check to make sure that it's less than 10%. And 14 divided by 10 or 0.10 is 140. So there are a few more than 140 men. So the sample is less than 10% of the population. And we need to make sure we explain why we did that, which is 10% of the population. Once again, we're doing that to check independence. The next thing was the new one, and the new one was differences are independent. Well, I don't know, but I'm guessing that Alex's change in heart rate was not impacted by trips and vice versa. So the difference in pulse rate are independent in that it is reasonable to assume that the changes in one's rate does not affect that of the other. And I know that that's an assumption, but we're going to have to make the assumption, but it's pretty reasonable. All right, the next thing is normality. And unfortunately, with normality, we have three ways to go about it. We can either they can tell us it's normal, which they didn't, or we can have 30 separate pairs or more, 30 more pairs, separate pairs or more, and here we only have 14 pairs. So it's not normal by central limit theorem. So the next thing I have to do is I'm going to have to do a box plot. So hopefully we've got the data entered. And here's the way what you need to do. First off, we need to combine this data. So we're going to go arrow up to L3, press enter. And then I'm going to go second 1 minus second 2. And the reason I did that is I had before minus after. And then I press enter and it populates it for me. All right, so now I have it populated for me and I'm going to press clear. Then I'm going to y equals. Make sure there's nothing on in y equals. That's the only reason I went there. Second quit. Then I'm going to go second, followed by stat plot. Press enter. Arrow to the left to make sure it's on. And I'm going to arrow to the right and select the one with outliers. Then I'm going to drop down. And I stored all my data in L3, so I need to press second, followed by the number 3. And then I'm going to press zoom, followed by 9. Now, every now and then, the calculator freezes it up like this, and you're going to press clear. And then zoom 9. And there it goes. Now, we have this data, and it's not particularly symmetric, but because it's College Board, we're going to say there are no outliers, and we're going to state that it is symmetric enough. All right, we're going to state that that's symmetric enough. Pause this for 1 moment. All right, so we press zoom 9, and we got this particular box plot. Remember, you can use the trace function to get the actual measurements. So this says it's -1. This says 1, 3, 4, and 8. Now, I always like to start off by drawing a sketch of it, the box plot, how I perceive it to look, and then I add labels. I don't usually use a scale, but I will label this as -1, this is 1, this is 3, this is 4, this is 8, and that's good enough. All right, so at this point, I need to calculate my X bar D and my SD. So I'm going to go stat, press the stat button in the middle of the calculator, arrow over the word calc, 1 variable statistics, second 3, and scroll through that really quickly with the enters, and I end up getting X bar equals 2.5714, and my SX equals 2.2434. I need to draw a picture of this, and my picture of this is going to look something like this. We claim that the mean was 0. That was our null hypothesis. So this is where that came from, the null. But we got a sample of 2.574. And our alternative hypothesis was greater than, so we're shading this way to -infinity. All right. Our equation is just t equals x bar minus mu s over the square root of n. We just drop some d's on it. And we have the probability that t is greater than our 2.57. That was our sample mean minus our hypothesized mean, standard deviation divided by the sample size. And when we did that, and here's how you do it: stat, arrow over the word test. Number 2 happens to be the t-test. I have data, so I want to make sure data is highlighted. My mean I need to set to make sure it's 0 because we're working with a difference. My data is an L3. And then I need to highlight the greater than symbol. And I end up getting a t equal 4.2887. And be really careful. We will never have a p-value greater than 1, but this one looks like it is. But if I look, I have -4. So that means I need 3 zeros in front. So this is really going to be 0.0004. So my p-value is 0.0004. All right. So p-value 0.004. And what that means is tenths, hundredths, thousands, 10,000. There's a 4 in 10,000 chance that I would get a sample as extreme as 2.574 or more extreme if in fact it's really 0. So in other words, there's a very small chance that it's really 0 because it's only 4 in 10,000 chance. So when we set our p-value 0.04 compared to an alpha, which they didn't give us, so we're assuming it's 0.05. Because the p-value is less, we reject the null. So conclusion, our p-value is whatever we calculated. We reject the null. There is sufficient evidence at alpha equal 0.05 to suggest that the true population mean differences in resting heart rate before minus after is greater than 0. All right. The greater than 0 came from this just came straight from our alternative hypothesis. And the true population mean difference, that came from our definition that we gave above. Now, my question is, did this exercise equipment seem to work? And the answer is yes. We have significant evidence at alpha equal 0.05 to say it worked. We believe that because we rejected the null. The null would be that there was no difference, that it did not work. The alternative was, hey, resting pulse rates went down. All right, they were greater before we started and less afterwards. So there is evidence to indicate that the exercise equipment worked. All right, on the next page, the next video will be the confidence interval for the same data.